Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the podcast we call Space Nuts. My name is Andrew Dunkley, your host, and with me, as always, the expert, Fred Watson from the Australian Astronomical Observatory. Hello, Fred.
Hi, Andrew. How are you going?
I'm going forwards. Ever forwards, doing my best stay on 2 feet and not let.
Well,
anything...
I thought you'd be going onwards and upwards.
That would work too, but other people are doing that, so I thought I'd be different. I'll just keep going forwards.
That sounds good.
The only thing going onwards and upwards is my golf score. So sometimes it's not a good thing.
Which you want really to go backwards and downwards, don't you?
You do. It's I blame the new handicapping system. It's based on the American system, and it's doing a lot of damage over here. I might point that out, but that's another story.
Another story. All right.
And one day an astronomer will fix it for me.
I hope so.
Today we're going to talk about the DNA of 340,000 odd stars. That's a lot of stars to extract DNA from, but I'm sure there's some kind of giant needle that's going to be used to do so. The TESS launch, which has just happened, well, it's happened our time. It'll probably be old news in a week or two. And we're going to try and tackle a couple of questions. One about photon redshift and living on Titan. Now, I think, Fred, that one's been spawned by a recent science fiction film, that question, but we'll get to that shortly. But yes, the DNA of 340,000 stars or thereabouts, what are we talking about here?
We're talking about a survey, and actually we're going to mention that word several times during this episode of the podcast, because surveys are a way of using whatever infrastructure or facilities you've got to explore very large numbers of objects. And in the case of the DNA of the stars, this is a survey taking place using the Anglo-Australian telescope, the 3.9-metre AAT, which is located at Siding Spring Observatory in northwestern New South Wales here in Australia. It is the telescope that I am perhaps most closely associated with because I used to be its astronomer in charge, and I'm still somebody who observes with it whenever I get the chance, actually usually on this survey. So that the telescope has an instrument which is called Hermes, and Hermes is an acronym which I won't bother trying to remember. But what Hermes does is it takes the light of round about 380 stars. Its maximum capacity is 400, but usually you're looking at 20 or so to get your calibration. 380 stars simultaneously, and the light travels down optical fibers and is passed into this Hermes instrument, which is a device called a spectrograph. And what Hermes does is it splits the light of each star individually into a spectrum. It means that there's a kind of rainbow generated, but we're focusing just on 3 very specific regions of the rainbow spectrum, not the whole thing from red to violet. It's just tiny little bits of it, which are looked at in great detail. And that allows the scientists who are doing this survey to look in detail at the chemicals which are present in the atmospheres of these stars. So it can sense actually up to 23 different chemical elements in exquisite detail because of the way the spectrograph is built. And okay, so you can do that for 300 or 400 stars at a time. What you then do is the whole sky.
Yeah, I was going to say.
Yeah, so the instrument actually looks at 2 degrees across, which is 4 times the diameter of the sun and 4 times the diameter of the moon. So it's not a big area of sky. So it takes several years to try and make measurements for 1 million stars, which is the target for the survey. Now, the survey itself has a very Australian name. It's called Galar. And you, as a country boy, will know that galahs are those pink and grey birds that you see hanging around the roadside throughout rural Australia.
Yeah,
but
yeah. We've got squillions of them here, and
squillions, yes, that's right,
as well as corellas and cockatoos, and there's some amazing bird life here. Yeah. I actually, just a side note, I actually love it when it rains and they hang off the electrical wires upside down to shower. They look hilarious. But that's another story too.
That is another story. There's plenty more stories about galahs as well that we could tell. But the galah itself, the survey galah, is an acronym, of course, and it stands for Galactic Archaeology with Hermes. So galactic archaeology is a discipline of astronomy that's all about trying to piece together how our Milky Way galaxy came into being and how it evolved. Now, the galaxy is this beautiful flattened spiral disk of about 400 billion stars. We're not going to look at all of them, but we want to get as big a sample as possible of these stars, and 1 million is the target of the project. To look at each star star by star individually to work out their origin, basically. It's all about where did they come from? What particular gas cloud did they come from? Because stars are born in gas clouds, and every cloud of gas has a slightly different chemical composition from the next one. But if you've got a gas cloud that gives rise to, say, 1,000 stars,
I see what you're saying.
You've got to. This is where the DNA comes from, because those 1,000 stars will all have, basically, they'll have identical chemical traces. They'll have fingerprints, if you like, that speak about the chemistry of the place where they were born. So that is one of the ways that we can piece together the history of our galaxy. But it also gives us the chance of doing something else, which is to look for the stars that were born at the same time and in the same place as our sun was. Yeah. Because our sun would have been formed in a gas cloud with perhaps 1,000 other stars, and they're all somewhere in the galaxy.
Essentially what you'll be able to do, once you've sort of mapped the DNA of say 1 million stars, then you'll be able to say, okay, that bunch there came from that gas cloud. You'll be able to backtrack on the migration of the stars over time.
That's correct, yeah. So you can do that. You can sort of play the movie backwards. To do that, you need to know the velocity of the star, and we can get part of that information from the Galar survey, but there is another survey going on which is being done from space. It's called Gaia, and Gaia is a satellite that is measuring very accurate positions of these stars, and when you do that over time, you can get a measurement of the star's motion. So with Hermes, with the Galar survey and the Gaia survey coming together, what you can do is not only find the chemical compositions of your stars, but you can also find their trajectory through space. And that allows you then to wind back the clock and see where they've come from. Yeah. So the first clue, if you've got a group of stars and you want to find, let's say, just for the sake of argument, because this is certainly one of the things that scientists are excited about with this survey, let's say we want to find the siblings of the sun's fellow stars that were born in the same cloud of gas. The first thing you're going to look for is stars that have the same chemical composition as the sun, and the Galar survey will let us do that. So you're looking for these stars with exactly the same elements in their atmospheres, in exactly the same distribution. It's the amounts that are the difference. All right, so you find them, and then you know the velocities of these stars. So it is just possible that you might be able to wind back the clock and find the common location where all these things came from. That's a much more difficult proposition because the sun is 4.6 billion years old. It goes around the galaxy once every 200 million years or so. So it's been around our galaxy many, many times in its history. And that makes it rather difficult then to unravel its trajectory over all those times, because there are different stars pulling on it and pushing on it and things like that. However, it is a great thing to be able to do, and it is possible that we might eventually be able to do that.
I suppose it's also going to open up maybe a Pandora's box, because over time, when you start piecing all this together, you're going to say, well, that star's there and that one's there and they're related. How on earth are they that far apart? What happened? Why? And I imagine this is going to happen thousands of times over.
I think you're quite right. And actually, that is one of the really exciting things about it. If you find a pair of stars which share the same motion, we have a word for that. We call them co-moving stars. So one star is co-moving with another. And you're absolutely right. They could be on opposite sides of the sky, as seen from our vantage point here in the solar system. But they're moving with the same velocity. And if they've got the same chemical mix of chemical elements, then that tells you that almost certainly they originated in the same gas cloud, even though they're now separated by great distances. And those distances might not necessarily be the result of some gigantic gravitational disturbance. It might just be the way, they've interacted with gas clouds and things like that in the galaxy that has caused them to undergo this separation. But I think that's a really exciting aspect of it.
Yeah, another one that I've thought of is binary stars. And, finding two that are unrelated and thinking, well, okay, what happened there?
Look, I was at a talk this morning, Andrew, where exactly these things were discussed. You should have been there making a contribution to it.
I would have enjoyed that.
Binary stars are one of the really interesting aspects of this whole process. We suspect that binary stars of the kind that we're looking for would have pretty well identical chemical compositions, because the thinking is that these two stars, and by binary, by the way, we should just explain the word. It means things that orbit around one another. So if you've got two stars that are considered to be a binary, they are orbiting around their mutual center of gravity. We would expect them to have the same chemical composition. Now, one of the problems is that stars like that, pairs of stars, are so close together that at the distance we are from them, we can't separate them into two. That doesn't, however, rule out knowing that it's a binary star, because you've got the possibility of sensing their motion. So if you've got two stars orbiting around one another, you can see from their spectrum that they are changing in velocity, and that tells you that it's a binary. And believe it or not, we give them a name. We call it the spectroscopic binary, because you don't see the two component stars, but you see their effect in the spectrum, the combined spectrum of the two.
Wow.
So these are techniques which are being applied to this Galar survey, the search for the DNA of all these stars. 340,000 is the number that were released yesterday in a catalogue which has the name DR2, and that's because it's the second data release. DR2 stands for second data release. That means the information is already publicly available, and people are already trawling through it, looking for all kinds of interesting scientific results.
Yes, and I'm sure we're going to hear more about it. And still a long way to go with this one too, by the sound of it.
Yeah, there's a few more years yet. It's a big survey. It involves a lot of observers. I'm one of them, but a lot of very exciting science as well.
Yes, indeed. All right, well, we'll keep an eye on this one, but we could learn a heck of a lot by the sound of it. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years, and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
3, 2, 1.
Space Nuts.
Now, Fred, we're going to talk about something that's been keeping you rather busy today because the TESS launch has happened. And, of course, media outlets all over the country have been trying to get a piece of you because it's pretty exciting stuff. And, of course, that's pushed our record time back several hours. Several hours. I've been here knitting.
I'm sure you have. It's a very nice jumper that you're wearing.
It's taken so long to get hold of you, I'm actually an expert at knitting now.
I'll believe that when I see it. I may say so.
But the TESS launch has happened. This is really interesting. Really interesting.
I think it is too, for all kinds of reasons. The first of which is that, yes, this is another survey, because TESS, whilst it's a delightful name, not quite as good as Galar, but not far off, TESS is an acronym for Transiting Exoplanet Survey Satellite. And the name really tells you everything you need to know about it. So exoplanet, that is the name we give to a planet orbiting around another star rather than the sun. Transiting tells you that the way we're finding that planet is by the fact that it transits or passes in front of the disk of that star. So as seen from our vantage point on Earth, this planet passes between ourselves and its parent star. And what that does is causes a very slight dimming of the light of the star, which is detectable by the cameras on board the TESS spacecraft. And the other two letters, the SS, survey satellite, well, it's a satellite, it's in orbit around the Earth, but it is a survey instrument. So unlike its predecessor, which was incredibly successful, and you and I have spoken about many times, which was called Kepler, unlike Kepler, TESS will look effectively at the whole sky. Kepler looked at a small area of the sky and found actually already 2,400 confirmed exoplanets and probably another couple of thousand on the way. Yep. Very, very successful. TESS will do the same as Kepler, but for the whole sky rather than for just a tiny little fraction.
Yeah, that's huge. I mean, the data that's going to come out of this, and I don't think we're second guessing by saying they're going to find just an incredible load of stuff. It's just mind-blowing.
Indeed, it's probably going to be tens, maybe even hundreds of thousands of planets beyond the Earth. So TESS is a fairly long-term mission. I think it's got a 2-year expected life. From where we are now, it will take about another month to get into its final orbit, which is itself unusual. The orbit of TESS is around the Earth, but it's a very elongated orbit. It goes at its farthest distance out to about the distance of the Moon, and then swings around and comes back in to pass close to the Earth. And the reason for that is to keep the spacecraft a fairly long way from Earth when it's making its observations, so that the Earth doesn't interfere with things. Yeah, get in the way. And then it swings back.
Look, we found Earth.
Yeah, that's right. That will be embarrassing. It has happened. People, astronomers are well known for finding things like the planet Jupiter and the planet Mars where they didn't expect to see something. But that's another story. So when it swings back to Earth, what it will do is download the data that it has been collecting while it's been a long way from the Earth. It will take 27 days to scan each block of the sky, if you like. It scans the sky in strips. Try saying that quickly. It scans the sky in strips, which run from north to south, basically, and spends 27 days looking at each strip. Then it will move on to the next one and the following orbit, and gradually build up basically a picture of the whole sky. It's not quite the whole sky. I should come clean and say it's 85%, but that's pretty well the whole sky when you compare it with its predecessor.
Yeah, well, that other 15%, that's the ghetto of the universe, and
could well be.
Who wants
yes.
to go there?
It's probably where the enemy is lurking.
Yeah, probably.
So TESS is a project that I think we'll hear a lot more of as the months go by, and I'm sure you and I, Andrew, will talk at great length about discoveries from TESS. What it's not doing, and this is kind of an important aspect, what it's not doing is looking for signs of life. It is looking for planets that could be habitable. So it will look for planets in the Goldilocks zone of a star, for example, that region where it's not too cold and not too hot, but just right for liquid water to exist. So we expect that it will find many of those, because we think there are at least 2 billion of those sorts of planets in our galaxy. And TESS is going to be looking at a big enough sample that it should find many habitable planets. What will then happen, maybe in a couple of years' time, the next big thing in space astronomy is the James Webb Space Telescope, the successor to the Hubble telescope,
which we spoke about a couple of weeks ago because it got delayed again.
Delayed, that's correct, to May 2020 as a launch date. Certainly no sooner than that. But the James Webb Space Telescope is ideally placed and ideally equipped to look in more detail at these exoplanets that will be found by TESS and look at the details of them, particularly the ones that we think are in the habitable zone of their parent stars, to analyse the atmospheres of these planets. It will be able to do that, and that is where we might start seeing the first signs of what we call biomarkers, markers of biological activity taking place elsewhere in the universe.
You and I have talked about this possibility, and here we are on the cusp of it.
In the cusp of it, yes, probably, still a couple of years away, but nevertheless getting excitingly nearer and nearer.
Now, you said 85% of the sky will be covered by TESS. I imagine it won't be able to detect every possible planet within that zone, because if it's using the transit system, there's going to be times where the planets aren't transiting certain stars, so you're going to miss those.
Exactly. That's an extremely good point to make. And the issue is that you're quite right, we won't detect all of them. But it turns out, and the statistics for this kind of thing were calculated many, many years ago, you do net a fairly high proportion, probably higher than you'd expect. You might expect to only find, perhaps 5% of solar systems that are exactly aligned so that you will see these transiting planets. But it's actually more than that. And I can't remember what the fraction is, and it depends on the type of star and the size of your planet. But still, it is well worth doing. And so you net, you probably get something like 20% of all the planets that are that are potentially discoverable by TESS. But as you say, they have to be transiting in exactly the right place.
I'm excited by the prospect of finding planets that may be able to harbour life, but I'm also more just as excited about maybe finding planets that we've just not encountered yet. I mean, we've seen strange things already, like gas giants that are seemingly too close to their parent star. What if we find a gas dwarf or something weird like that? I reckon that'd be exciting.
Yeah, and I bet it's on the cards as well. That is exactly what the scientists expect. They expect to find, the whole sort of range of objects that we know about is constantly being extended by these perhaps steadily more and more bizarre objects. I think they'll find planets made of solid gold and diamond planets and things like that, as well as the gas giants, the ice giants, the super Earths, the super Neptunes, the whole array of things that we've found already with Kepler. I'm sure we'll find more of those and perhaps even more exotic items, which you and I hope we'll be able to talk about. One final thing to say about TESS, Andrew, which is, once again, SpaceX, which actually built the launch vehicle to put TESS into orbit, has done its trick of landing the booster rocket, the launch vehicle itself, on its ocean platform, that little barge that's floating in the Atlantic Ocean, which has the wonderful name of Course I Still Love You. That is floating there and catching the rocket as it comes down to land, and it did that successfully this morning. After the launch, they got their rocket back, which is fantastic news for SpaceX, and they're doing a great job.
They are indeed, yeah. It's an exciting time to be an astronomer, Fred.
Very much so. It always was an exciting time.
Yeah, but it just keeps getting better and better.
It's getting more and more.
Yeah. All right. We've got probably a couple of years of data to look forward to on this one. This is Space Nuts. Andrew Dunkley here. Fred Watson there.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Time now to tackle a couple of questions. We're going to try and knock off 2 today. The first one from Kim Forrest at Kalamunda in Western Australia. Hi, Fred and Andrew. I'm an avid listener of your podcast and have it on regularly while I'm commuting. A few weeks ago, you answered a listener question about photons of light being redshifted as they travel across the universe. As I recall, Fred, you indicated the photons leaving their parent star lose energy as they travel due to the redshift they experience, lower frequency, longer wavelength photons having less energy than higher frequency, shorter wave photons. You suggested that this energy is simply lost to space as the photons travel. My question is, a lot of preamble in that one, my question is, how does this loss of energy relate to dark matter? There must be gazillions of photons traversing each cubic kilometre of space, all of them losing energy as they go. Could this contribute to or account for dark energy, or alternatively, is it dark energy that is actually causing the photons' energy loss? Over to you, Fred. I love the question. I actually understood it.
It's a great question. That's right. So the question is, how does the loss of energy relate to dark energy? Not dark matter, which is something else completely. Mm-hmm. Dark energy is, just to recap on that, that's the energy which we think is possessed by space itself, that is pushing the universe to expand ever more rapidly. So the expansion of the universe has been known since 1998 to be accelerating, a very, very unexpected result. And we now know that the energy of dark energy, that energy that is going into pushing the universe apart, when you look at the total mass energy budget of the universe, it amounts to 75%. So dark energy is by far the biggest component of the universe. The mass, which is the other 25%, is divided into dark matter, which is about 20%, and normal matter, which is actually rather less than 5%, it's about 4%. So stars, galaxies, gas clouds, all the things we can see, and effectively photons of light as well are part of that what we call normal matter, amount to only 4% or thereabouts of the budget of the universe.
That's amazing.
That really is
because if you did a street survey and say how much of what we see in the universe is actually, what percentage, people would tell you, 80, 90%.
They would.
Would
they? That's right. But it's not. There's a lot more besides. The trick is we can't see it. And we call both dark matter and dark energy dark because we don't know what they are. It's not a very good name. They're really invisible matter and invisible energy, but we tend to call them dark. So just returning to Kim's question, the preamble is absolutely correct. Yes, as light travels across the universe, it's stretched in wavelength by the expansion of the universe, and basically because of that, loses energy. And as Kim says, when we discussed this a few weeks ago, my comment was that energy is basically just contributing to the overall energy budget of the universe. It goes into the space around it. But, and here's the big but, that amount of energy is infinitesimally small, even talking about the gazillions of photons that are going through every cubic kilometre of space, and Kim's absolutely right that is the case. The energy that they're losing is negligible compared with dark energy. So it cannot be that energy is the dark energy that's forcing the universe apart ever more rapidly, because the numbers simply don't stack up. The energy lost by photons losing energy is much, much smaller than what is going into pushing the universe apart, the dark energy itself.
Well, you probably answered it when you said that everything we can see, including light, makes up only 4%.
That's right.
So it could not be making up the vast amount of other stuff that's out there in terms of energy. Yeah.
Yes, that's quite right. So it's a great idea, but the arithmetic doesn't work, and so we're still on the hunt for dark energy. We believe it is an energy that space itself possesses, so that as space gets bigger, the energy gets bigger as well, and that's completely counterintuitive. Normally, you think of a pump or something like that, where you increase the volume of something, and then the energy goes down because you've increased the volume. But in the case of space, it doesn't seem to work that way. The energy actually increases with the size of the space. So what is it? We don't know. Particle physicists have had a go at it. They get an answer that is 10 to the power 20 times too big. If their answer was correct, the universe would have ripped itself to pieces, billions of years ago.
Yep.
So it's not something that we understand. Dark matter, I think we do have a solution to in sight. I think it'll turn out to be some subatomic particle that we have not yet encountered, but we've got a pretty good idea where to look. With dark energy, we haven't a clue where to look. It's some fundamental property. It probably will incorporate a rewriting of the textbooks in a very big way, but they have not yet been rewritten.
Because we just don't know yet.
We don't know, that's right. And so
someone
it's up to you to find the answer.
Someone will pick up a broken bottle and look through it and go, "Oh, dark energy."
Yeah,
and they will have accidentally invented a dark energy lens. That's what I reckon.
They might indeed invent a dark energy lens, and we might know about it. But at the moment, we really don't know.
Okay. Kim, thank you for the question. Hope we didn't answer it for you, because we didn't, really. Because we don't know. Let's move on. This question, I think, has been prompted by a recent movie, but I could be wrong. But there's a movie, a science fiction film out at the moment, Fred, called The Titan. And it's based on Earth reaching a point where it's unlivable, and the only way to save the human race is to alter our DNA so that we can live in the atmosphere of Titan. That leads me to the question from Henry Zane Long. Thank you, Henry. With Titan, do you think that the gaseous atmosphere, most of it being liquid, would the gases mix? And would we be able to live on it if they did mix? Because I know alone nitrogen would kill us as a liquid. Yeah, it's a pretty nasty place, really. I'm surprised they did a science fiction film about moving to Titan when we could it'd probably be easier to terraform Mars, but Fred doesn't want anyone to do that, so they had to make a movie about going to Titan instead. So
I'm not sure the movie makers were listening to me all that much.
I'm pretty sure they listened to you and then decided, we better change our plans. Yeah. But I've actually seen that film, and it's pretty awful. But what about Henry's thoughts on making Titan livable?
Well, I think you can probably rule that out. The main problem with Titan is its average temperature is minus 180 degrees Celsius, so that things that are nicely gaseous here on Earth are actually liquid there, like hydrocarbons such as methane and ethane. So it has clouds of methane and ethane in its atmosphere. They precipitate. You get raindrops of methane and ethane, which pool in lakes and seas. And we see all that. Those were all discovered by the Cassini spacecraft in the past decade or so. But regarding the atmosphere, so even at Titan's frigid temperature, there are some gases that do remain, or there's some elements that remain gaseous, and one of them is actually nitrogen. So nitrogen, which is the main constituent of the Earth's atmosphere, is also the main constituent of Titan's atmosphere. I think there's rather more of it than there is on Earth. We have, if I remember rightly, it's something like 75% nitrogen, maybe 20% oxygen, or perhaps a bit more, and a few percent of the other things, argon and things of that sort. But nitrogen is the biggest component at about the level of 70 to 75%. On Titan, I believe it's more than that. So most of Titan's atmosphere is nitrogen, but the other gases in it would indeed mix. The ones that aren't liquid, the ones that are still gaseous at the temperature of Titan. So they would mix. We would have to have a big influx of oxygen to make Titan's atmosphere breathable. But even then, even if it was breathable, you'd still have the problem that you're breathing air at minus 180 degrees Celsius, and that does nasty things to the membranes of your larynx as well as your face and everything else. So my guess is that even with the most amazing equipment for trying to make Titan resemble the Earth, it's really a long shot. Your best bet is to wait for about 3.5 billion years, because in that time in the future, the sun will be much bigger. It will have warmed Titan up to a nice, reasonable temperature. If it's still got those gases there, yes, we might be able to breathe the atmosphere by then. But I'm not holding my breath.
Boom, boom.
Boom, boom, yeah.
Or we can just speed up DNA technology and turn humans into Titans.
Oh, what a nice one. I think despite being full of admiration for that horrible pun, I think the better way is to fix things here on Earth, because we cannot afford to make the Earth unlivable. It is too precious a resource, because it's the only place in the universe where humans can live, at least that we know of so far.
Yeah, and we really aren't in a position to move. That's the problem.
That's the other problem. That's right.
So, yeah, we do need to fix this planet, and we need to do it fast.
But a great question from Henry, and
yes,
thank
indeed.
you very much.
Thank you, Henry, and keep the questions coming in. We've got a bit of a backlog at the moment, but we'll try and get through those in time to come. And Fred, next week is episode 100. It's crept up on us. What are we going to do?
Well, we need to have a party, don't we? I think what we should do.
We will answer 100 questions.
We could do all kinds of things. We could answer 100 very short questions.
If we could get 100 questions, that means all of our audience has to ask 10 each.
Yes, that's right. Actually, I think they all have to ask. They've got to ask 50 each, haven't they?
Look, we'll put some thought into it, but 100 episodes strong next week. We're looking forward to it. Thank you, Fred, as always.
Great pleasure, Andrew, and I'm looking forward to episode 100 as well. I think we should involve as many of our listeners as we possibly can and see how we go from there.
That would be nice. All right, We'll talk to you soon. Fred Watson from the Australian Astronomical Observatory, and from me, Andrew Dunkley. Thanks for listening. Thanks for your questions. Thanks for telling your friends about us, and don't forget to keep doing that and keep in touch, and we'll catch you next time on Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast. Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.